Ma'am, live started.
Thank you. A very good afternoon to all the participants for Social Networks course, which is being offered by Professor Sudarshan Iyengar and myself, Dr. Poonam Saini from Punjab Engineering College on NPTEL Swayam. So this is the second session, which is going to be online. For this, we have planned to cover two parts. For the first part, we are going to have insight upon clustering and will relate it to social networks, how clustering is important for social networks. And in the second part of this session, we will focus on the visualization of centrality measurements through tool which is called R tool, which is a very famous statistical tool. We are going to make all visualization of whatever centrality measures you have learned on the course. So starting with this clustering and social networks, first of all, we should know why we need clustering, and specifically when we are talking on social networks or we are talking of social media. So all of us know that social media, it provides a staggering amount of data to us, right? And if we want to extract knowledge from this volume, it requires a lot of automation as well. Now, when we have to compute very quickly over this data, it becomes a challenge in order to design all the algorithms as well as the architectures. And recently, we have been very well aware of a popular micro blogging site or trend, which is responsible for a large amount of information dissemination. The most prevalent micro blogging services is Twitter, as we all know, which is a very popular tool for short, frequent communication between nodes, right, or between end users. So Twitter users, they tweet about any topic, the status or any event, and they follow others to receive their own tweets as well. So anyone can use this Twitter, and then they can talk about daily activities, they can seek some information. Now, when we are observing such a high usage of these sites like Twitter, so many of the business, many of the research group, they have started analyzing such tweets, and they can have a possible evaluation upon the connections as well as the predictions, right? Because the complete social media is all about predictive analysis, and whatever the algorithms, whatever the measurements we have through social networks course, we can use these measurements, we can apply, and then we can talk on the possible predictions, possible patterns which can come from these nodes, from this data and other things. So we have in literature, there are a lot of APIs, there are a lot of tools which have been developed, and they can predict some future events as well. So as the importance of this Twitter, it keeps on rising day by day, then the research also in the field of information science, in the field of corporate, in the field of marketing, in the field of civil society sectors is also emerging a lot. So now what we do in social networks, we try to develop or a network graph, right? We consider all the users to be node on this graph, and then we take some edges between these nodes which attributes to the characteristics. For example, if we talk of Twitter data set, we can say following, retweet, these are all characteristics which attributes and which comes from the edges between the nodes. Now these tweets can be grouped into clusters, right? And we can use some unsupervised methodology, we can use that, and there are a lot of clustering methods for these kind of approaches, like flat clustering is there, which we can always use, and then we can make them grouped into clusters. Now we realize when we have to analyze this tweet, right, it is very challenging because we have very short text here, we have non-conformance to some grammatical rules as well. So clustering tweets effectively will be a very like research and a very challenging research, and then we have to have some sort of functionality into the system which is through which we are able to actually derive this sort of grouping. So clustering plays a very important role when it comes to analyze of such social media platforms. Clustering indirectly, we can say it's the community detection, which is again a very popular tool to analyze and to do some sort of research on complex networks. Now, in literature, there have been many methods for accurate community detection. For example, we can use spectral clustering, right? Spectral clustering is one of the promising clustering method which can accurately detect all the communities from a given set of social network. Now, when we have to do clustering of a social network graph, so we have to identify communities. As soon as we have to identify the communities, we have to understand that there are certain steps which are need to be followed so that we can acquire the accurate grouping. We have a precise grouping of the nodes in a given cluster, in a defined cluster. The first very step to get into this clustering for social network graph is to identify the distance measurement for social network graphs. So if you are applying some standard clustering methods to social network graph, you have to define a distance measurement first. So when you have the edges of the graphs, right, these edges, all of us know that these edges have some labels, and these labels can be used as a distance measurement depending upon what type of representation you have done for these labels. But when these edges are not labeled, sometimes we have unlabeled edges as well. For example, you have a friends graph, right? So you have studied friends graph, and there is like not very much information, and we cannot define a very suitable distance into that. So the first instinct is to assume that the nodes are close if they have an edge between them, and the nodes are distant if they do not have any edge between them. Therefore, we can say that the distance, which is defined by a metric called d in x and y, which means from node x to y, the distance will be 0 if there is an edge, and that distance will be 1 if there is no such edge which exists between the nodes. And we can again use some other two values, like we can use 1 or infinity, as long as the distance is closer and whenever there is some edge between the nodes. So the very first step is to identify this distance measurement. In the second step, we have to apply some standard clustering methods, right? There are some general approaches to clustering, like we have agglomerative clustering, which is called hierarchical clustering as well, right? So if you are doing something on social network graph, so when we do hierarchical clustering of such graphs, so what we do, we start combining some nodes which are connected by an edge, right? So ultimately we will eventually be getting edges that are not between two nodes of the same cluster. They would be chosen randomly and they will combine the clusters to which their two nodes belong to, right? So this way we can have cluster, we can successively repeat the steps so that we can get finally a set of cluster which is hierarchical in nature, and the choice of adding the nodes into these clusters could be random, right? Because whatever the distance we assume which is represented by an edge is going to be same for hierarchical clustering or agglomerative clustering, right? Similarly, we have another approach like point assignment approach as well, right? So we have to apply a standard clustering mechanism, and that's where we need clustering. If we say why we need clustering in social network, because once we are defined with a distance measurement between the nodes, then obviously we have to choose one efficient clustering method which is going to create the groupings based upon some objective criteria, and then we can further work on this network graph. The third step is to identify or work upon the betweenness parameter. So all of us have learned this betweenness parameter very clearly into the classes, right? So as soon as we start with standard clustering methods, there could be different problems as well, because every clustering approach or any algorithm which we are going to apply comes with some overhead complexity as well, right? Sometimes we have some specialized clustering techniques which are designed or developed to find the communities in the social network, right? So we can use any standard clustering method and then we can decide or we can find out the betweenness. So we define betweenness between two edges as the number of pairs of nodes between these two nodes, such that every edge lies on the shortest path between these two nodes. So if you assume two nodes x and y, so you have to come up with an edge a or b which lies on the shortest path between these nodes, right? To be more precise, we can say that because there are many paths. So if you think or if you visualize any social network graph, so you can see that in order to reach or in order to communicate your message from one node to the other node, you have different paths which are available, right? But with the centrality measurements, with this betweenness, we can always find the shortest path. We can always find or identify an edge which lies on the shortest path between any given two nodes, right? And for example, if you play golf, so when we say a high score is there, it is always bad, because it suggests that whatever edge A, B, it runs between two different communities, it means A and B does not belong to the same community, right? So this way we have to work out on the betweenness measurement, and after that we can apply, in the next step we can apply certain algorithm we have learned for, like, to exploit the complete betweenness factor. We can use Girvan-Newman algorithm, right? So we have to calculate the number of shortest path, because once the problem comes to identify the shortest path, then you have to calculate what are the number of shortest path which are going through each edge. And for that you can apply Girvan-Newman algorithm, and you can use this method where we can say that every node is visited at least once, and you compute the number of shortest path from that node to every other node, right, to each of the other nodes which go through each of the edges. And this algorithm is going to use BFS, right, which start at some node, right? So we can easily use this algorithm, and you can have the edges identified between levels to be called as DAG edges. As you all know, it's directed acyclic graph, and every DAG edge will be part of at least one shortest path. So we can apply the simple concept of this algorithm and DAG, and we'll be able to know the number of shortest path. And then finally, we can use the betweenness in order to identify the communities. So we see that this clustering is very, very important in order to identify. And as soon as we have to work on this clustering, then we have to get a little bit insight on what type of clustering we are given with, and then we can apply accordingly according to the application or the project we are going to develop. So given any set of nodes in any network, we can use a clustering algorithm. We can classify every node into some specific group, and in theory we can say that the nodes which are in the same group, they should have some similar properties and features, or if we are using some sort of data analytics on this network data which we have extracted through the social media platforms, and then the nodes in different groups will have highly dissimilar properties, right? So clustering is method of some unsupervised learning, and it's very common technique for statistical data analysis as well, which can be used for different fields. So social media analytics is one of the application we can start with. Now we have hard clustering, where we group the data items such that every piece is only assigned to one cluster. So this is known as hard clustering. And then we have soft clustering as well, where we can group the nodes such that an object can exist in multiple clusters. So you can see there could be a friends network, where we can say that for a particular network of my, like, friends cluster, I might have some of my friends, right, which are exactly only one time they are into my cluster of my community. And sometimes I may have a soft clustering where one of my friend could be a part of the another cluster as well, which is my friends friend community cluster, right? So there could be common friends as well, and there could be a cluster where altogether we have a single friend in the network. Now, if we see the importance of clustering and classification, so we have to understand that whenever we have to extract value from this large social network, right, which could be in which could come in structured or unstructured format, because as soon as we try to extract these data sets, right, for example, if you extract Facebook data set or any social media data set, so you have all sort of possibilities. Depending upon your objective criteria, you decide that whatever input features I was looking for is present in very well format, and that could be a structured format. But sometimes if you are trying to sort out some sort of problem and the relevant features are not included into the data set, could be an unstructured data set. And because we have huge volume of unstructured data sets around us, so we need to partition everything into logical groupings, and these logical groupings are nothing, these we call as clusters, right, the community clusters. So we can take a comprehensive view of the large social network data sets, we can form some logical structures which are based on the findings, and we can do a deeper analysis into the data set. So if we talk of classification and clustering, so we have to say that these two terms, they are like not similar to each other. With classification, we have number of classes which are already known into the data set, into that social network data set, which has to be grouped. Sometimes with clustering algorithms, we say there is no predefined concept, right? Like what should be the appropriate number of clusters, how we are going to rely upon the clustering algorithms. As I said, there could be standard clustering algorithms and there could be specialized clustering algorithms. So you have to identify which algorithm is going to support your analysis in an optimal way. And you have to also learn from unlabeled data set many a times. So these two terms can be taken into a form. And if we say cluster in simplest form, it's the set of data points which have some similar attributes, as we already said. So clustering algorithms are going to group all the data points or all the nodes into different clusters based upon the similarities, where we have different applications. So we had one question on the group about the projects which we can implement using this knowledge from social network course. So see, there are diverse applications where you can use this measurements which you have learned, where you can use the knowledge graphs, where you can use the link prediction algorithm. So there are a lot of applications where these things can be implemented. Like you can have a recommender system where you can build an academician's citation database, right, based upon how many times the paper has been cited or so. So that can be one possible application where you can have the information retrieval, and then from that network of academicians, you can always work upon the citations database, creating that, and then look for the recommendation based upon whatever pattern you have identified from that data set. Similarly, you can have disease classification, right? You have medical sciences data sets which you can always take into, and then you can apply these measurements, again knowledge graphs, to identify a particular sort of disease. Then you can identify the customers as well. So customer classification is very, very important when we are doing a lot of business, because a lot of social media data analytics is being carried out for this marketing domain a lot. So when we do marketing research, when we have to do viral marketing specifically, so we need a lot of customer classification, we need a lot of data, we need a lot of patterns which can be extract from this data set, and then we can always classify and say we can target the specific customers for a particular product or a particular market, whatever development we were targeting towards. Similarly, we can have environmental health risk assessments as well. So we can analyze every kind of like the real life or the societal cause around us using this knowledge from the social network data sets and all. Now, what is clustering? Organizing the unlabeled data into similarity groups, we can call them clusters, and dissimilar nodes into the other cluster. So we have the cluster as collection where we have similarities as well as dissimilarities. If we talk to the historic application of this clustering technique, then in 1850s there was a massive outbreak on cholera, and then a London physician, he was able to plot the location of all these deaths, and location indicated that the cases were clustered around certain intersections where there were some polluted wells, and then it exposed the problem as well as the solution. And then he formulated the theory that the spread of cholera was due to some dirty water. So you can see this was the very first application of clustering which came up with this, and it was able to sort out the pandemic as well, and then some sort of solutions were being proposed. The very first question when we start with clustering comes as, what do we need for clustering? Now, for clustering, the very first measurement is the proximity measurement. Either we want to know the similarity measurement or we want to know the dissimilarity measurement. So as I said, when we have to start any sort of clustering mechanism on given social networks data set as well, so we have to understand that we start with some distance measurement identification. So we know that there is some similarity measurement which is going to tell us the similarity between two nodes given xi or xk, and this similarity measure is large if xi and xk K, these two nodes are similar. Similarly, we have dissimilarity or distance measurement, which is given by distance between these two nodes, which will be small if they are similar. So we have large d and small s, which means if the distance is large, then similarity measurement is small. If the distance is large, then we have small d. So if similarity measurement is large, then we will have a small distance. So this is the first thing which we have to talk on, the proximity measures, where we calculate the measurement of similarity and dissimilarity, right? So because we have to do on a number of data mining techniques. For example, here we are talking of clustering. Sometimes you might be working on nearest neighbor classification, as you have done in the course. For two nodes, you have to identify which is the nearest neighbor to a particular given node, and sometimes you have to work on anomaly detection as well. And in this case, we can say the learning of proximity measurement is very important, talking on similarity and dissimilarity factors. The second thing which is there to talk for clustering, or which is the requirement for clustering, is criteria function. Now, what is the notion of clustering? Whether we have formulated a good clustering or a bad clustering. So this notion is very, very relative. We cannot, or it's like we cannot ever say that whatever clustering we have come up in the first iteration of a given learning, or whatever data set we were trying to work for, has come up with a good clustering. Maybe there are number of iterations which have to be performed sometime in order to come to a near optimal cluster. So we cannot say that a given cluster being created is a bad cluster, or a good cluster being a relative notion of this clustering. We cannot evaluate, but of course there are certain matrices which we can always use to identify whether a particular cluster is near optimal or not, whether we have formulated, whether we have been tried, we have been able to club the similar items or similar nodes, or the friends with similar characteristics into a common cluster, right? So that way, where we have some criteria function which we can always use. And the third thing is algorithm to compute clustering. So whatever objective function you have decided, whatever criteria function you have decided, you have to have an optimization. You start with some optimization, you start with the criteria function, and then you start to minimize, or you want to maximize the maximize upon that criteria function. So that way we need proximity measures, we need a criteria function, and we need an algorithm to compute clustering. So these are three things which are required. If we talk on distance or dissimilarity measurements, very famously in literature, you will find that we have these two distance, which is Euclidean distance and Manhattan distance. So we have Euclidean distance given any two nodes. We can always summate the difference of the distance between these two nodes, and then we can square it and root it, and we'll get the Euclidean distance between two given nodes. Similarly, we have Manhattan distance, which is the absolute summation of the difference between the distance of two nodes, which is an approximation to Euclidean distance as well, but it is somehow cheaper to compute in comparison to the Euclidean distance. So there are different, we can say, the dissimilarity measurements or the distance measurements which exist. There is some Silhouette index, there is DB index, there is Dunn index, right? So it depends what sort of evaluation you are doing while you are formulating the cluster. Depending upon that, you can choose some sort of cluster, this distance measurement. Now, when we say cluster evaluation, which we already said is a non-trivial task, it's a hard problem. So we can at least rely upon these two parameters, which is intra-cluster cohesion and inter-cluster separation. So when we say intra-cluster cohesion, we mean the compactness of that cluster which we have created. Cohesion measures how near the nodes in a cluster are to the cluster centroid. So basically, we'll try to calculate the cluster centroid, and then we will look which nodes are nearer to this cluster centroid, right? And that could give the cohesiveness into that cluster. And the very commonly used measure is sum of squared error, which we can always use. But of course, this sum of squared error sometimes might not be used as an optimal evaluation parameter, because there are certain limitations, or we can say there is some sort of regularization parameters which are not added when we are doing this simple measurement of sum of squared error. For that, we can look into the details for this SSE and its related residual error, like whatever the problems are with this SSE. Similarly, the second evaluation parameter could be isolation. So when we talk on isolation, we say inter-cluster separation, where we mean that different cluster centroids should be far away from one another. So because when we have to talk on cohesiveness, we have to calculate the cluster centroid, and then we have to see if the nodes which are present into the cluster, how far are they from that cluster centroid. Similarly, inter-cluster separation is very important to say that whatever dissimilarity nodes were there, whatever the node has some dissimilar feature in with respect to the other node, they have been kept into different clusters. So that is important to know. And in most of the applications, as I said, cluster evaluation is very trivial. So it's like the expert judgment which can only tell you whether it's a good cluster, or by experience you can come to know about these formation of clusters. Now, another interesting question could be how many clusters. So if you are given a social network graph and assume that there are some 500 nodes for that social network graph, and you want to do some sort of analysis, you are doing it for some real life societal implementation or application development. So how many clusters, if you are trying to again identify the communities in that graph, how many clusters would be best to create? Either it would be 3 cluster or 2 cluster or 5 clusters or what. So the possible approach is we will start by fixing the number of clusters to k. So randomly we will choose a number, and then we will fix the number of clusters to some k, and after that we can find the best clustering according to that criteria function. So as I said, we need a criteria function, because based upon that only we can say that whatever the optimization I was looking for, my criteria function, I can decide that this could be the number of clusters. As we say again that anything which is going to be implemented, and the algorithms, they always come with some sort of complexity or overheads always. So cluster formation always comes with overheads. Number of clusters means more space required, and then more sort of communication intra or inter cluster in order to achieve your objective. Because at the end of the day, what is required after formulating these clusters, you are going to have some sort of communication. Again, based upon that communication, you will again improvise upon the patterns you are trying to predict, because this is a dynamic network nowadays. So we should not say that the person who was trying to browse one particular website for long is still after 2 or 3 years we can give same sort of recommendation to that individual, because the person or the individual has now shifted to another website and start browsing, and based upon that browsing history we have to improvise, or we have to revise the recommendation, right? And that's how the dynamic networks poses a challenge again for this kind of community detection, and then making these community detection more automative in nature, more adaptive in nature, more reconfigurable in nature. As soon as there is some shift of the nodes from one cluster to the other cluster, because we cannot confine these nodes for long into a cluster if this is a dynamic network, dynamic social network graph. So in that case, we say that as soon as there is some sort of transition of nodes from one cluster to the other cluster, in that case we have to optimize, we have to make the models learn again, and then they will propose some sort of predictive patterns which are optimal in nature. So how many clusters can just start with a random number, and then you can fix that clustering according to your criteria function. This is a very broad schematic view on clustering techniques. We can say the clustering techniques could be hierarchical, they could be Bayesian based, and under hierarchical there could be divisive approach. There is one approach called agglomerative approach, which I just talked on. So it's very important. From this graph, hierarchical agglomerative is one of the approach which has been frequently used for the analysis of social network graphs. Similarly, for partitional based techniques, we have centroid method, model based method, graph theoretic method, and spectral method. Under Bayesian, we have decision based clustering method, we have non-parametric clustering methods. So we can see that there are a lot of techniques which can be like identified under different categories, and based upon your criteria function, based upon your application chosen, you can decide what sort of clustering method is going to give you the optimal cluster formation, and then you can decide upon one. So hierarchical algorithms, they will simply find the successive clusters which uses the previously established clusters as well. As we said, these algorithms can be either agglomerative or they can be divisive. Either they will use bottom up approach or top down approach. Agglomerative begin with each element as a separate cluster, and then successively it merged them into some large clusters. Similarly, we start with whole set in divisive algorithm, and then we try to divide. So altogether we will take the complete social network graph of 500 nodes, and then we will try to bring out or divide it into smaller clusters. Whereas in agglomerative, we'll start with, say, a separate cluster. We decided that we'll have one cluster of 10 nodes first, and then or one node or two node, and based upon the criteria function. So criteria function, specifically if I talk here in terms of network, so we say that if you are working on some sensor nodes, so you can say that the nodes having kind of some certain battery limit or battery power will be clubbed into one cluster, and then other than this threshold, within this range, it will be clubbed into the next cluster or so. So this is how we can decide upon one criteria function. Similarly, for a friends network, we can decide on a criteria function that a particular characteristic or attribute which is being fulfilled by these nodes will be put into this cluster only. So this is how we can decide on the function, and we can try to formulate based upon the agglomerative and divisive algorithms. Similarly, we have partitions, we have Bayesian algorithms where we use some sort of posteriori distribution, priori theory of or posterior theory of probability, and then partitional can have all type of clusters at once, and then we can use the partitions techniques like centroid or like that. So there are many popular clustering algorithms. I have just named few of them here. We have k-means, mean shift, dbscan, agglomerative, hierarchical, though there are many clustering algorithms which are very popular, which have been used by the social network communities, the researchers a lot, in order to come for this clustering or combinatorial detection given social network graph. And today I'll just brief on k-means and agglomerative hierarchical from these two, from the popular clustering algorithms. So talking on the k-means clustering algorithm, so first of all, let us know that how this clustering will be beneficial if you are doing some content promotion. Again, I'm talking of some application. If you are doing some recommendation, if you are doing some sort of content promotion, so you can use this, like you can put all the websites, or we can say that whatever websites are there, they can put all the people in some bubbles. Specifically, we call them clusters, and then whosoever shares some sort of similar activities or features on that website. So this is how the recommended content can be, like it can be learned on the existing users, and then we can have some sort of insightful pattern for the other users which are going to enter into that bubble. Because once you have created one cluster, then anyone who is entering into that cluster, you can easily identify that the particular person or individual has the attributes or characteristics of this cluster only, and then you can easily again recommend or do this kind of. So this is going to create a lot of ecosystem of that website, as well as soon the person will be placed into that particular cluster when it's going to enter into that network, right? So k-means is it's the first partitional clustering algorithm which was given by McQueen in 1967. Here we assume that we are given some set of data points, say x1, x2, and then we have vector which belongs where these data points belong to this vector, and R is your number of dimensions. Now the k-mean algorithm, it partitions whatever the data you have, right? For example, given that again social network graph, the nodes which you have been given, it will partition these nodes into k clusters. Every cluster will have a cluster center which is known as centroid, and k can be specified by the user. As I said, we can randomly start with this. So building on that idea, k-means is just a clustering algorithm. It's going to use the distance between the points as a measurement of similarity, which is based on k average, right? Average means we are going to use mean. So that is why it is known as k-means clustering. So here we specify the number of clusters, start with that random number k, and then you can initialize the centroid. You can first again like you can initialize the centroid by shuffling this data set, and then you can randomly select k data points for the centroids without replacement, and then you assign each data point to the closest centroid. After this is done, you will recompute the centroid, because as I said, there could be a change in the cluster memberships. So you have to recompute again and again to analyze which nodes or which data points are nearer to this centroid which you have chosen initially, right? This is the cluster center, or we call this initial centroid. And after this, we will recompute the centroid. We will use the current cluster membership. And if some convergence criteria is not met, we will repeat these two steps. As soon as the convergence criteria is met, we will stop, and then we will say a particular cluster has been identified. So this is how this k-means clustering algorithm will work. What is the convergence criteria? If we say we have to converge, we have to stop somewhere. So when we are going to identify that this is the stopping criteria or the convergence criteria, when we are able to identify that there is no reassignment of data points to different clusters. If we know that now the number has reduced drastically of the nodes to be put into a given or identified cluster already, then we can stop this. We can say that we have identified a cluster with the optimal number of nodes to be put into that cluster, or we can say that there is no or minimum change of centroid, because we are recomputing centroid, and if there is no change into that centroid value, so it means, or there is a very slight change, we can say that now the cluster is formulated well and we can stop here. And if there is minimum decrease in the sum of squared error, so as we said, this is also a popular measurement in order to understand whether we have achieved the dissimilarity, this measure between two nodes or not. So if this sum of squared error, which is we can say the Euclidean distance between any given node X and the centroid of a given cluster. So if that has achieved, if we are able to identify the distance, and if we say that this distance has the minimum decrease, right? So there is the least decrease in the sum of squared error. So it's the distance between any given node X and to its centroid of that cluster, right? So whatever the cluster centroid is, so with that, with respect to that cluster centroid, whatever the distance of a particular node is, if that has minimum decrease, we can say we have met the convergence criteria. So these are some like stopping criteria we can decide upon when we have to stop for clustering. So this is just an execution visualization of k-means clustering, where we say that we randomly initialize the cluster centers. So we can see here we have some sort of data sets or data points, or we call these nodes. There are some nodes here which are identified in green like bubbles. Then we have these centroids which have been calculated. So initially we started with some random number, and we have chosen, we have calculated, and then in the second run we'll determine the cluster membership, because as soon as we have these three centroids, based upon the distance of these nodes from the centroid, we can decide that which of these nodes will fall into this cluster. So we can see that if we have these green nodes here, so we say that these will fall with cluster C2, the centroid C2, because the centroid and the distance of this node, it has the least decrease or sum of squared error, or there is minimum reassignment, and we have to repeat all these steps until unless we are able to identify that a particular node can move to some other cluster, if in case we are able to attain that convergence criteria or not. So we have to determine the cluster membership for every given input. We will re-estimate the cluster center, because it's not there initially you have started randomly with this cluster center, but you will recompute this cluster center as well. And as soon as you will recompute, you will find that there is some sort of like shifting of the cluster centroids, and then you will identify that different clusters which we have started with initially with these centroid, it has shifted to some new nodes, or few nodes have been they have been moved to the other cluster, right? So this is the result of first iteration, we can say, on k-means. And this way we have to do a lot of iteration, and as soon as all the convergence criteria are met, we can stop, and then we can say that we have achieved the clustering of the nodes in a given graph or in a given network. So you can see after second iteration, again recomputation of the cluster is being taken place, and then after this will become the result. So there is a slight, we can see the movement of the nodes from one cluster to other. In case already naturally the clusters which were created initially with some cluster centroid, they have that natural convergence criteria sometimes. But again, because when we work on large nodes, right, large number of nodes in a social network graph, so we have to do a lot of iteration so that finally we achieve the optimal cluster, right? So when we say we are using this K means, the strength is that it is very easy to understand and implement. It is very efficient as well in terms of time complexity. We can say the complexity is linear because here we have TKN, where N is number of nodes, K is number of clusters, and T is number of iterations. And based upon that, we can have a simple linear complexity O of N for this, because K and T, right, K and T are very small. Initially we said we will start with a very small K, it could be 1 2 3 or so on, right? Similarly, number of iterations, they would be small in case we naturally met the convergence criteria also, and that leads to a very less complexity in that case. And K means is very popular clustering algorithm. It also terminates at local optimum, right? If we are using sum of squared error, so we try to say that it terminates at local optimum, which specifically means that we are not able to achieve the solution from the exhaustive set of possible solution. It's not a global optimum, because global optimum is very hard to find out because of its complexity. So local optimum specifically means that whatever the available options were, right, local to that particular algorithm, we are able to find out the most optimal from that, right? We are not able to identify in totality. So we have sometimes exhaustive set of solutions which always exist for a given problem, but we are not able to work upon that set, and we are not able to identify from large exhaustive set the global optimum. But of course local optimum is always like it's always possible to identify from a given local set of solutions, we can say, or a specific set of solutions, we can say. There are certain weaknesses of k-means as well. It is only applicable if mean is defined for categorical data. Sometimes we have data in the form of like names. For example, if you are working on some data set where you have the name of the city associated with a particular node, so it could be Chandigarh, Mysore, Delhi. So it means we have to have some different method where k mode, right, can be used, which is represented by most frequent values. So in case if we are not using mean, we can use mode, and user again has to specify this k. And the main weakness of this k means is the sensitivity to outliers, because every data set might have an outlier, right? Call it a social network data set or any sort of data set which you are trying to work upon. So we have a lot of outliers which we say are the nodes which are very far away from the other nodes, or we can say there could be, because in a given friends network as well, there could be few nodes, right? They might not be able to connect to any of the cluster because they do not carry any sort of similarity or dissimilarity, right, based upon that threshold which we have decided to put a particular node into a given cluster. So in that case, we call that particular node to be an outlier, and it could be an error as well. As soon as you try to record some data, and if it is wrongly recorded, then it becomes an outlier, and there are some special data points with different values as well. So there are certain weaknesses, but k-means always comes with the advantage of fast execution, right? It can always compute the distance between the nodes and the group centroids easily, right? And we have a very less number of computations which are involved. This is just to show you about the outliers. Like we have sometimes the outliers, and if we try to include these outliers when we are doing this cluster formation, it might lead to some undesirable cluster. So you can see on in the first graph, we have this outlier which is very far away, and if we try to formulate a cluster with this, so that will lead to a very bad clustering, right? So that can lead to undesirable cluster at the end. Similarly, if we avoid, because the simplest like technique is to avoid the outlier nodes if they are less in number. But if they are large in number, then you have to understand there are a lot of techniques, statistics which have to be learned and which have to be used in order to work out for these outliers, because we cannot every time ignore outliers if they are very large in numbers, right? So we can remove them, and we can do some sort of random sampling as well. So safely we can remove, we can monitor if at some point of time these nodes try to enter, because again, as I said, the dynamicity of network always it could lead to some of the nodes to get participate at some later point of time. And when the node participate, then your algorithm, your model learning will change, will have to be changed, your approach has to be changed, and the final outcome, the final prediction will definitely be going to be changed as soon as new nodes enter into your this analysis. Then you do some random sampling, you can choose some small subset of data points, and then you can select, if you select an outlier, the chance of selecting that particular node, outlier node, will be very, very small. This is just to show the sensitivity to initial seeds. Initial seeds is the name given to centroid. Centroid is also known as initial seed. So we can see if we have random selection of centroid. So sometimes there could be different formation of the cluster at the end of the iterations. So from the first or the left hand side graph, we can see from this given node, whatever iteration 1 and 2 has resulted will be in this shape. The cluster formation will be like this. And if we have like the random selection of this centroid is like in the right hand side graph, it's like green star and red star, it is in this shape, or it is in this form, or like we will have this kind of cluster formation at the end. So it will depend upon the selection of the initial centroid, right? Wherever you select, accordingly the cluster will be start formulating depending upon that distance measurement. There are certain special data structures, right? The k-means algorithm is not suitable for them. For example, if you are able to identify two natural clusters in the left hand side graph, so it is not good to apply this k-means clustering, because as soon as you try to apply, then you will get some sort of this hyperspheres, right? And this is the formation which will lead to this kind of formation. And k means variant is there, which is called k median. So instead of k means, we can also use k median, and we can recompute the group center points using the mean. Instead of using mean, we can use median vector of the group. This is very less sensitive to outliers because of using that median, but it is low as compared to the k means for large data sets. So there is variant as well, which you can use depending upon your choice. After K means, let us talk on hierarchical agglomerative. It uses top-down or bottom-up approach. Bottom-up algorithms treat every data point as a single cluster at the outset, and then successively it merge the pair of clusters until all the clusters get merged. Bottom-up, whereas it is also known as hierarchical agglomerative clustering, or HAC very famously, and you will find in most of the social network graph analysis, hierarchical agglomerative clustering is very famous approach, and it is represented as a tree or dendrogram, and root of the tree is unique cluster which gathers all the samples, and then we will be left with one sample only. So here you can see that we have this graphical illustration of HAC, where we start treating every node as a single cluster, and if there are some X nodes in the data set, then you will have X clusters, that much number of clusters you are going to formulate. So you select some distance measurement, and then based upon that distance measurement between two clusters, you can decide. Every iteration, you will combine two clusters into one. So as you can see, at every iteration of this execution of these nodes, so you will combine two nodes together, and after that, this will be trying to formulate some sort of tree or dendrogram, and based upon that, finally you will be given some clusters which have been formulated, and based upon Euclidean distance, this is going to work out. So this is the graphical illustration for HAC, and this is what we have seen into the visualization. You will select a distance measurement, and every iteration you will combine two clusters into one cluster. The policy is that two clusters are to be combined, which are combined are selected as those with the smallest average linkage. So if there is some average linkage which is small, so you can always combine these two clusters, and this can be used as the average linkage policy between any two given nodes. So it does not require to specify number of clusters as we had in k-means. Similarly, the algorithm is not sensitive to the choice of distance measurement, and you can use this as for the nodes or the set of data set which has some hierarchical structure. It has lower efficiency, but it's not comparable to k-means, which has linear complexity. It has a complexity of O n cube, and the time complexity is of this order. And this is all about the agglomerative and k-means. So in the next part, we are just going to take you towards R tool visualization for few of the centrality measurements we have covered in the course.
Hello everyone. In the next part of the session, hello everyone. In the next part of the session, we'll be using R tool, using IPython library. So R is a programming language and software environment tool for statistical computing and graphics. And about something about IPython, it is majorly used for data visualization and analysis. It can handle both directed and undirected graphs. It is a collection of network analysis tools with the emphasis on efficiency and portability and ease of use. So IPython can be programmed in R, Python, or even with C or C++. So how we can install the packages? Let's see. First, let's see this. So how to install the IPython library? You need to write install dot packages and then the name of the package. So as the name of the package is IPython, we will write I, then Python. So in order to install a library, we need to choose a CRAN mirror. So you can choose any CRAN mirror based on your comfortability. So I am using this Australia Melbourne. And so let's wait for this to get installed. Okay, so it's saying that it's not available. Let's check for another mirror. It is iGraph, sorry. So iGraph is getting downloaded. So it is downloaded. So let's first load the iGraph. After installing the package, you will load the iGraph. So once the iGraph has been loaded, what you can do is you can create graph from edge list, data frame, or adjacency matrix. So it includes some. It includes some classical random graphs such as Rini model, GNP, and GNM graphs, along with models like preferential attachments and small world models. So any model that you have learned use in your lectures, you can implement them using this iGraph module. Also, so once it is done, you can also load a pre-known graph, which is like this. This is the function that you can use for loading pre-known graphs. I'm loading a karate club graph. So there is some problem with iGraph. So here what you can see is for creating a graph, what you can do is you can create a empty graph with vertices and having letters A, B, and C and no edges. After that, you can actually add edges to the graph and make it to a string, to a ring, and then after that, you can convert it into a layout for checking the graph in the form of layout as a possible plot. After that, you can plot the graph using plot function. Also, you can check one of the existing graphs as well. This is the function for this sample g underscore gnm, and giving the number of nodes and along with the edges. So the number of nodes here are n equal to 100. With 100 nodes, you'll be getting a graph with with 40 edges. So once you will plot this, you will get a graph of 6 vertex size, and there will be no label on the vertex. Further, let's see another possibility of how to use another existing graph and calculate degree, centrality measures, and along with hubs and authority vectors that you have read in the lectures. So for that, I'm loading a graph, which is a karate graph. Then after that, I'll basically calculate the degree of the same as you are using an R tool. So an R tool basically assigns the value of the variable using this arrow form. So what you will write is a degree, then an arrow, and then a degree function. So this will load the value of the degree function to the degree variable. So after that, you can create a histogram of the for the graph as well, to see what are the various degrees available onto the into the network. Along with that, what you can do is you can basically calculate the hubs and authority scores as read in the lectures. So in order to calculate the hub score, what you will do is you will write hub dot score and get the only the vector of the same. I only need the vector of the hub score. I'll write hub dot score and then the vector. For authority, I'll use authority dot score and then the vector. In order to calculate in order to calculate the betweenness centrality, what I'll do is I'll basically use a function known as betweenness, and along with the graph. So this graph G can be a directed as well as undirected graph. Along with this, I can use edge betweenness as well. So I can use a layout, and the layout which I'll be using is a Ringgold layout, and I'll be plotting my graph using this layout. So all these centrality measures which I've told, that is a degree, a hub, a betweenness measure, or a edge betweenness, can be plotted on a Ringgold layout. You can use other layouts as well. So it will depending on your choice that you want to use a Ringgold layout or any layout that you want, and you can further play with these layouts and check which layout can be suitable for your domain or your problem statement. So in order to plot a degree, what I'll write is plot.igraph g comma layout, and the main will be degree. So it will be plotting all the degrees. Similarly for hubs, I'll be plotting the vector of the hub. Here the vector of the hub values is very small, so I'll be multiplying the values with 15 in order to plot it on properly on the graphs. So I'll be multiplying it by 15. So it depends on your choice, whatever number you want to take as the multiplication factor, you can take it and you can multiply uh, the vector with that, because it will further affect the vertex size. So according to this, you can actually choose the multiplication factor. So now this will plot the hubs vector. Similarly for authorities, I'm taking the authority dot scored vector and multiplying it by 15. And along with that, I can plot the betweenness measure as well. So betweenness measure is a big number, so I'll be decreasing it by a small multiplication factor and choosing a 0.25 multiplication factor, where my main is betweenness. So using this, so here you can see, using these commands, I can just calculate and put it into a variable. That is, this degree will be a variable, will be a vector. This hub, authority, betweenness, and e-betweenness will be a vector. Whereas in order to plot and see how it actually works and how that how the graph differs according to the degree, hubs, and authorities, and between this, I can actually plot and basically I can check how my whole graph looks like and further save the checkpoints and further save the weights. So this is how basically iGraph is used for R. I think this it gave a brief introduction to iGraph and introduced you to a different tool using R. And till now in the lectures you have used NetworkX using Python, and you can even use this iGraph use in Python as well. So there are a lot of research directions and work that you can do using iGraph and NetworkX. So with this, we will like to conclude the lecture.
So thank you all of you for joining the online session, and all the very best for the exam. And the exam will be MCQ type as you have asked in the chat box. We have already answered to many of the queries. And regarding the queries for disadvantages, limitations of social networks, similarly how it impacts the mental health, I have shared two research articles. They are very famous, you can go through them, and I'll also share these articles on the forum as well. And the assignments have to be practiced upon very well, so that you are well aware about the pattern of the exam. It will be similar to the assignments, right? So all the best to all of you. Thank you all of you.